Now, you might have learned already that you can create atomic vectors simply by writing down the objects that you're interested in case you want to create a vector of length 1, and that you can use the function c to create atomic vectors of basically arbitrary length. But sometimes that might be cumbersome to do in a manual way. So there are some useful helper functions that allow you to create atomic vectors that you use frequently, like sequences from one vector to another one, like from 1 to 10. And there are easier ways to write down all the elements and concatenate them with C. And this is what you will learn about in this video. And aside from these very useful practical helper functions, you will also learn about indexing, so how you can access or substitute single elements of atomic vectors with many elements. And you will learn about the super important concept of vectorization, which allows you to speed up computations on many elements considerably by actually placing all these elements into one atomic vector and then apply a function to the overall vector. So that is why this operation is called vectorization. It's a very particular feature of R, and it is one reason why R can be very, very quick in doing certain computations that involve many different elements. But let's start with common or often helpful helper functions. There are a number of situations that you encounter frequently and that have to do with creating certain kinds of atomic vectors. Here we will deal with one of the most frequent ones of them. First of all, we are dealing with situations in which you need to create a sequence of numbers. Then we will deal with a situation where you need to concatenate words. And finally, with a situation where you need to repeat certain elements. And we will encounter some useful helper functions that help you out in each of these situations. There are a couple of more, but we focus on these three here. Now, sequences of number. Think about, for example, you want to create a sequence from 1 to 10. You could do so by writing 1 manually. But this is obviously very tedious, in particular if that sequence becomes longer and longer. So instead of doing this, you can actually, this works by the way, but you can also use the useful function called sec, which generates a sequence. Now sec you can use in a variety of different ways, depending on the arguments you use. The standard way sec works is, if you just pass in two numbers and you execute the function, is to create a sequence from the first number to the second one, evenly spaced. So in this case, we actually can substitute the quite longish manual creation of a sequence from 1 to 10 from line 2 by just writing sec 1 and 10. That's actually not the most transparent way to use sec, because that is the default way it works. The default way is that it uses the keywords from, or the arguments from, and the arguments to. So that is actually what happens in the default value. But you can use sec in a variety of ways. You can add another keyword to sec. Which is called by. And by you can actually specify the length of the steps between the numbers. So the default version is that by is set to 1, but you could also set by to 0.5, and then a sequence with spacing of 0.5 is created. So that is quite useful in some instances. Useful as well is another variant of sec, where we actually use not the keyword by, but you use the keyword length out. Here you determine the length of the vector that is actually produced by sec. So you could say, okay, the vector should have length 7. If you execute that, you again get a sequence from 1 to 10 of length 7. So we can verify this by actually applying the function length to this. And it verifies that actually the result of the call of length with the optional argument length out equals 7. So another thing that is sometimes very useful is to create a vector that has the same length as another one. So for instance, we can think of, we have vector 1 that contains the elements 1, 6, and 9. And then we want to create an index vector that is a vector from starting with the number 1, being evenly spaced with steps of 1 until the length of vector 1. So in our case, we can create an index vector for vector 1 simply by using the function sec, right, along with, and then point vector 1. We execute this, and what we get is an index vector that actually starts with 1 and ends with an integer indicating the length of the original vector, and we have our index vector for our vector 1. That is actually very useful in practice and helps you to save a lot of time. Another helper function that comes in very handy when you want to concatenate words is the function paste. So the function paste works as follows. You write paste, then you write down part of a character string. So in our case, let's say we write file, and then think you want to create the names file 1, file 2, file 3, file 4. Then you now just use the function sec to create a sequence from 1 to 4. If you press enter now, what R does is to concatenate here the first string you gave it, file, together with a sequence you give it as a second argument. So you have file 1, file 2, file 3, file 4. Now, this is useful if you want to create a sequence of file names, for instance. But if you create file names, it's usually not a good idea to have these white spaces in there. So what would be nice actually to have an argument that tells R what to put between this initial character here and the sequence you provide paste as a second argument. And fortunately, you have that with the argument set. It has a default option, which is the white space. So if we write down this, we get exactly the same result. This tells R that the separation between this string here and the sequence you provide should be white space. But you could also provide, for instance, an underscore. And if you press enter now, you see that now R concatenates the initial string with a sequence and as a separator uses an underscore. That is very useful in practice. Sec also has some other arguments like collapse and recycle. It's probably best to just try that out, but in practice the most important thing is separator. So that comes in very handy if you want to create atomic vectors of type character by combining some things. And the nice thing here is that you can put everything in here, be it a variable name or a sequence or whatever. So we could also use the vector 1 that we've created previously. And now you see here that it uses 1, 6, 9, which are the elements of the vector we created before. So that is quite useful in practice. And another thing that you might often want to do, and that doesn't depend on whether you want to create a character vector or a double vector or whatever, is to repeat certain elements. So think, for instance, we want to create a vector that contains 5 times a certain character string, like cool, for instance. Then we could write cool, but that is actually not very efficient. So what you could write instead is use the function sep, provide the string or the object that you want to repeat. And then as a second argument, simply the number of times you want to repeat this object. So in our case, it would be 5. Now, if we execute this function, we get exactly the same result as before. And that is usually very useful. It also works with other things. Like, for example, if we want to create a vector with 10 missing values in it, we just write rep na10. So we will encounter a number of situations where especially this creation of a vector with many missing values that are then later filled by certain operations we execute to be very, very useful. So while these helper functions I was just talking about are not essential, they are really useful to make your daily life as a programmer much more convenient. The next important thing you need to know about atomic vectors is how to access single elements of a vector that contains several elements. So for instance, here we have a vector called vbase. It's a character vector and it contains 4 elements. Now imagine you would like to access only one of it, say the third element. In this case, you just write the name of the vector, then you open square brackets and you provide an integer with the index number of the element you want to access. So if we want to access the third element, we here write 3. And if we now execute this, you see that it actually gives us the third element of the vector. Important in R, the first element of a vector gets index 1. In some programming languages like Python, the first element gets index number 0, but in R, the first element gets number 1 as an index. Now here you figured out that the third element in this vector actually gives us the string second. And we see that here in the vector we have the string second twice. Now imagine we would like to correct this. Then we can actually use indexing to replace elements of a vector, because we just now assign a new object to this vector. So in this case we could actually replace the third element with a character string third. If we execute this, and we look again at our vector, we now see that this has been replaced. So you can use indexing to replace elements of an atomic vector. What is a little bit dangerous, though, is to add or to reassign indices of a vector that do not yet exist. So imagine we look again at our vector here. We see that it has 4 elements. Now imagine we would like to add a 6th element. Now in this case we could write vbase, provide the index 6, which doesn't exist yet. We assign the character 6th. If we execute this now, we actually see that R has added the 6th element, but because indices need to be in sequential order, there now needs to be a 5th element, and R added a missing value here at this stage. And this is sometimes not exactly what you want, because you might just want to add something to the vector and you actually thought the vector would have had 5 elements, but in fact it had only 4. And then this NA is not exactly what you wanted in the first place. And there's also another potential problem if you use indexing as a mean to concatenate vectors. Now to see this, imagine we have the following 2 vectors. And we would like to concatenate them. Now, you might think that actually one option to achieve this is to take vector 1 and to add vector 2 as a third element to vector 1. Because vector 1 currently only has 2 elements, and as a third element we want to add the vector 2, which has 2 elements, so we might think that in the end we actually end up with a vector of the 4 elements 1, 2, 3, 4. Now let's check what actually happens in this case. Here we get a warning message. So the number of items to replace is not a multiple replacement length, meaning that actually we only provided an index for 1 element, the third, which doesn't exist yet. But the replacement value here, this one, has 2 elements, and R cannot do that. So it cannot nest indices in this sense. So what actually comes out of this operation here is that R only uses the first element of the replacement vector. And this is not exactly what we wanted, because we actually wanted to concatenate the two vectors. In this case, if you really want to concatenate vectors, the best option actually is really to use the function c, which in fact stands for concatenate, and then provide all the vectors that you want to concatenate in the first place. Now, if we do that, we need to redefine them. And now have a look at vector 3. We see that exactly this has happened. So if you want to concatenate more than one vector, especially if one vector has more than one element, then you should use function c. But I recommend you to use this index replacement here only to replace existing indices. This is definitely the safest way to go and to achieve what you actually want to do. If you want to concatenate vectors, always use the function c. And now we come to the last important concept when it comes to atomic vectors, namely actually one of the main reasons for why atomic vectors are so popular in R, despite their restriction that they can only contain elements of the same type. But this restriction actually allows for a concept called vectorization, which is extremely useful. Now, to illustrate this, think about this vector 2 here. It contains the numbers from 1 to 5 in steps of 0.5. And now imagine you actually want to compute the square root for each of these elements. Now you could do this in principle by calling the function sqrt on each of the elements of the vector. So you could call it on v2, the first element, you get it. Okay, square root of 1 is 1. You could apply it to the second element of v2, get the square root of 2, and then you could actually concatenate all these results into a new vector. And you could do this with actually all the elements of the vector, and then you would get the square root for each of these elements. Now, this is very tedious for you to write. It takes a lot of time, and while it is not very important in the context of just computing the square root, it actually also takes a lot of time for the computer to execute this task. Whenever you actually want to apply the same function to all elements of a particular vector, you shouldn't call the function separately on each element, but you should vectorize your operation. And to vectorize an operation means actually to make sure that all the elements you want to apply the function to are stored in an atomic vector, and then just do the following, right? sqrt v2, execute this, and you here get the square root for each of the element of the vector v2. This is terribly efficient in terms of computation, but it is also straightforward to implement for you. So this is much easier than to write this actually for each of the elements there. You could, in principle, also use something called a loop, something we encounter later on, where you write a certain number of keywords in a row to apply a function to each element of a certain input vector. But that is actually not that preferable. So what is really the best way to apply the same operation to many elements is to store all these elements in an atomic vector and then call the function with this vector as an input. This is called to vectorize a certain operation, and it's one of the main advantages of R, and it makes it very easy to apply the same operation to a wide variety of inputs. So vectorization is definitely something you should remember, and something you should always think about in practice. You should always ask yourself, okay, what I'm currently doing, is this something I could vectorize? If you really do that, you will save yourself and your computer a terrible amount of time. Now, at this point, it's probably best to step back a little and have a look at the following intermediate exercises. Do them, and if you want to make sure you did them correctly, check out the solutions in the video.